And what the next talk is about another important component, that is RF components that will be part of a system on chip and challenges in it. And it is my great pleasure to invite Dr. Prameela to this session. Welcome, Prameela. It's an honor to
You,
have you
Tripti, ma'am.
here.
Yeah.
So I'll just introduce you. Dr. Prameela B is an educator and a researcher with about 18 years of teaching expertise in VLSI domain. She has earned her PhD in RFIC design from Cochin University of Science and Technology. Uh, Currently, she is working as a senior staff engineer at Silizium Circuits Private Limited, Fab CI in IIT Hyderabad. She's involved in the design related to GNSS and 5G front-end modules, RFIC for navigation and IoT in various technological nodes. I am really happy to invite you over to this session and hope people get a good exposure to RFIC design and their and the challenges through interaction with you. Over to you, Prameela.
Thank you, Tripti, ma'am, for the nice introduction. And good afternoon, everyone. And once again, I congratulate the Department of Electronics, CUSAT, for hosting such an online FDP on secure and intelligent system on chip. Today, my topic of presentation is RF front-end design challenges. Hope my audio is okay.
Yes, you're audible, and if you make it full screen, video is also.
Yeah.
Yeah.
So
Okay.
I will turn off my video for the time being so that bandwidth issues are not there. So yeah. So we'll slowly start because it's a Saturday evening. I will rush through some of the important aspects of RF design. So as we all know, the wireless communication is driving our day-to-day activities, especially the mobile phones, then the navigation system, then asset tracking systems, home automation devices, automotive applications. So designers are always trying to incorporate more functionalities and features into devices. So here comes the significance of the term integration, where more and more components, that is more and more functionalities, are being incorporated onto a single chip. So in fact, we are trying to reduce the number of off-chip components so that the designs are cost effective. And I think all of us are familiar with the scaling of technology, especially in the CMOS technology. So as a result of the scaling, the power consumption is reducing and the speed of the system increases. But along with that, there are design challenges. Design complexities are there, more second order effects, parasitics comes to see. And there are a lot of trade-offs in the system specifications. So slowly, I will move on to the core theme of the presentation. So this is the overview, the RF spectrum and applications, analog RF mixed signal design overview, RF transceiver, then MMIC foundries and the related PDKs, MMIC design flow, LNA design, package simulation, and summary with the design challenges. So hope you are all aware of the radio spectrum, the radio wave spectrum spreading from 10 kilohertz to 400 gigahertz. A lot of applications are there in this radio spectrum where these MMIC designs comes into see. So mainly our company focuses on this 1 to 50 gigahertz frequency, where in the say in the S-band spectrum, we are having the Wi-Fi GPS applications, and in the lower frequency, we are having the GNSS applications. I will just scroll through the different frequency ranges connected to these applications. One is a SATCOM. the role of SATCOM, satellite communication in global communication. So these are some of the satellite communication applications in aeronautical communications, telecommunications, military, maritime, navigation, etc. So once we start a design, we should be able to analyze what are the different frequencies associated with these applications. So as far as the SATCOM frequencies are concerned, mainly now we are doing the designs in the KU and KA band. KU and KA band frequency range, where KU is from say 11 to 12 gigahertz, that is a downlink frequency, and the uplink frequency is from 14 to 15 gigahertz. And KA, it is the uplink and downlink frequency that is in and around 28 gigahertz. It is uplink frequency. And again, SATCOM applications range from this L band, S band, C, X bands also. So just to scroll through the different frequency bands and the naming of the bands like L band, S band, C band, etc. And again, coming on to the 5G, as we all know, the 5G is driving the current activities. For example, IoT, industry, manufacturing, healthcare and critical services, enhanced mobile, smart vehicle and transport. So coming on to the 5G frequency bands, usually we categorize it as sub 6 gigahertz and above 6 gigahertz, that is a millimeter wave bands. So the lower band, it is the sub gigahertz band. It is having the limited capacity, but with larger area coverage. And the mid band is from 1 gigahertz to 7 gigahertz. And mostly it is for urban deployment. And the higher bands, that is a millimeter wave frequencies, that is above 24 gigahertz. It is having the high data rates, but the coverage will be limited. So we'll be concentrating on all these 5G frequency bands. Basically, now designs are coming up in the higher frequency band, about 28 gigahertz. And another application is the Global Navigation Satellite System, that is GNSS. The different satellite systems, like you are aware of, is GPS, GLONASS, BODO, Galileo, QZSS, IRNSS. So these are specific for certain regions, or it is common, available globally, like GPS. It is available globally. GLONASS is available globally. IRNSS, that is available for India, that is specifically for Indian navigation purposes. And basically, this GNSS systems, the bands are, it is in the L1 and L5 band. Basically, L1 band is in and around 1.5 gigahertz, and L5 is 1.1 gigahertz. So these are the bands associated with the GNSS. And coming on to the world of VLSI, I would like to classify VLSI into three broader domains. One is the analog domain, the digital domain, RF, or the mixed signal. So basically, to differentiate between this analog, digital, and mixed signal design, some of the circuitries in the analog category, it is the op-amps, band gap reference, ADC-DAC drivers, current mirrors. These all comes under the analog design area. And basically, it deals with the voltage or current domain. And we have to take care of the parasitics while designing in the analog domain. And parasitics, it affect the performance of the system. We have to take care of this parasitics while designing in the analog domain. And digital domain, normally it is the microprocessor, logic gates, memory, counters, FSMs, etc. In that digital domain, the highlight is that automatic place and routing tools are there, so that the layout will be handled mostly by this tools, automated tools, and the parasitics are handled in the timing closure part. And coming on to the RF and mixed signal design, the basic components or the circuits with respect to this mixed signal or RF domain is low noise amplifier or LNA, then mixer, VCO or PLL, power amplifier, then filters, balloons, etc. And the main parameters how we analyze the design is through S parameters, scattering parameters, and impedance matching should be taken care of. And Smith charts are very important while designing this RF and mixed signal design. So this is an overview of how we categorize the analog, digital, and RF designs. Basically, RF design is something very different from analog design. How you design an op-amp, it is entirely different from how you design a low-noise amplifier or a mixer. And as you all know, application-specific integrated circuit, that is ASIC. This is basically ASIC. This is an example of an AND gate IC. And application-specific integrated circuit, basically, the circuit, in that circuit, each element is carefully handcrafted. That is the peculiarity of the analog design, where the layouting is done manually by the layout engineer. And a huge design effort is involved in the layouting of an ASIC. And because this performance of the analog part is very important, we have to take care of all the parasitics while doing the layout of the application-specific integrated circuit. And compared to digital design, analog and RF designs are very, it needs a huge human effort, because the tools available, they are not that much automated. Human intervention is needed in each and every part of the layouting of the analog and RF designs. So this is a basic mixed signal system. Here you can see an antenna. This is a front-end module. Front-end module, I will come into what is a front-end module. So front-end module, for this is an transceiver. We are having a transmitter and a receiver. So when we move on to the receiver part, you can see a low noise amplifier, then a current sampler. Then in the transmitter part, you can see a power amplifier. And here going on to the left side, you can see the digital baseband processor. Okay. So this is the layout of the complete mixed signal system. And here you can see in this transceiver, the digital baseband that consisting of the DSP, microprocessor unit, memory, and all other digital components are all over here. And as far as a transceiver chip is concerned, you can see 70 to 80% of the area is consumed by this digital part. And all the other analog and RF parts come into the small area. But again, the design of this analog and RF section is very crucial, because it decides the basic performance of the transceiver. Okay. Moving on to what is a wireless RF front end. So from the antenna, this is a receiver part. The antenna receives the small signals. It takes in the small signals, and you will be having an amplifier as the first stage. That is a low noise amplifier, followed by a filter, then a mixer to down convert the frequency. So basically, this is the RF front end in the receiver part. And a more good view of the RF front end, you can see this is the receiver channel antenna. You are having a duplexer. That is it consists of two filters. One filter, the signal will be going on to the receiver part. This is the LNA filter and the mixer. And in the transmitter part, you will be having an up converter, that is a mixer, then the power amplifier, filter, then to the antenna. So this is basically an RF front end. Basically, it consists of a low noise amplifier in the receiver part and a power amplifier in the transmitter part, along with some switches or duplexes. Okay. And this is an RF transceiver structure in detail. And these structures actually differ according to the applications. Because this is not a hard and fast rule that you should have the filter in before an LNA, or you should have a filter after the mixer. These all depends upon the specification or the application of the system you are designing. And basically, this is a structure of an RF transceiver, where you're having filter, LNA, mixer, and the PCO, the oscillator, it gives the LO frequency to this mixer. Then you are having a filter, then into IF amplifier. If needed, you can place a balloon, and there is a track and hold amplifier if you want. Then going on to ADC and to the FPG. And here, this is the transmitter section where you are having the DAC, the digital to analog converter. And again, if you need, you can place a balloon depending on whether it is a dual differential or single-ended. And filter, mixer, that is an up converter, then filter, then a power amplifier. And the power amplifier output is given to the antenna for transmission. So basically, this is the receiver section and this is the transmitter section. So as I said, the RF front ends has different architectures depending on different applications. So here, these are the different architectures used in defense and aerospace. This I have taken from the Corvo site. And you can see for military and civilian radar applications, there is a switch in between to switch between the transmitter and the receiver part. And there is an LNA and power amplifier as the front end module. And there is a driver amplifier, mixer, etc. And for defense and aerospace communication, again, the architecture is different. For SATCOM, again, the architecture is different. Electronic warfare, it is again different. So the system designer, there will be one system designer who will be fixing what should be the architecture for a specific application. So anyway, but in all the transceiver architectures, there will be a low noise amplifier, which is the first stage for receiving the signals, and there will be a power amplifier for transmitting the signals. Basically, these are the RF component design considerations. You have a low noise amplifier, as I said, and the parameter, main important parameter is the noise figure. For power amplifier, the main important parameters are the OIP3, the third order intercept point, then P1 dB, 1 dB compression point, then the efficiency, power added efficiency, then the gain. For mixer, the conversion loss, frequency range, etc. For filters, loss in dB, then rejection, pass band, return loss, everything is important. So these are the parameters once we move on to the RF various component designs in the RF area. And moving on to the MMIC designs, that is monolithic microwave integrated circuit design. So in MMICs, the entire RF or microwave circuit, like amplifier, mixer, filters, these will be fabricated on a single semiconductor chip. And basically, it will be designed for high frequency operation. That is above 1 gigahertz designs. We'll call it as MMIC designs. And the main technology types are, we can go for silicon based, that is CMOS. You can go for CMOS SOI, silicon on insulator, then silicon germanium BiCMOS. You can go for gallium arsenide based designs. You can go for gallium nitride based designs. And for filters, you can go for SAW or BAW filters. So this is a comparison of the different technologies that can be used for MMIC design, comparing the CMOS, then MESFET, HEMS, etc. So moving on to the higher frequencies, usually designers prefer the gallium arsenide or gallium nitride based designs because of the additional advantage, which I will be presenting in the upcoming slides. So here you can see with in response to 5G, usually designers go for gallium nitride and gallium arsenide based designs for high power amplifier because these GaN and GaAs, they will be having high power density. So they go for GaN and GaAs based designs. And for amplifiers, SOI, CMOS SOI and SiGe can also be a choice. And for RF filters, BAW and SAW technologies are used. And for RF switches also, we can choose between different technologies, and everything depends upon the how the different technologies, the efficiency of the technology depends on. And finally, on the GaN, previously the GaN based designs were used for defense only because it is very costly. GaN and GaAs based designs are very costly compared to CMOS. So now what we have seen, the trend is the designers will be going for the CMOS based designs because it is easy to integrate between the different modules, and it is also cost effective. But nowadays, designers are moving on to the GaN and gas-based designs because of the higher efficiencies and because of the competing gain and efficiency of the GaN and gas technologies. And especially GaN, they are having higher efficiencies. And because of this high efficiency, it results in the reduction in the system power consumption. And also, it leads to improved battery life because of the lower power consumption. So nowadays, even if it is costly, for high performance, designers make use of GaN technologies for their power amplifiers and for their switches, mixers, etc. And because of their higher power density, it leads to smaller size and miniaturization and easy integration. So here you can see comparison between gas and GaN. Compared to gas, GaN is having 82% size reduction and 4 times power density. So because of this, you can go for miniaturized designs, and nowadays it is easy to integrate also. So GaN technology, we can conclude that it reduces the design complexity, and it is essential for the success of high frequency commercial markets because the efficiency of the efficiency and performance of the system is very important, so that the chips that comes out of the market, we are able to compete with the existing leaders. And coming on to the foundries, semiconductor foundries, we call it as fabs. So basically foundries, they provide the infrastructure and capabilities for fabricating the chips. Once the GDS file is ready, we send the GDS file to the foundries or the fabs, and the fabs will be fabricating the chips for us. And these foundries, again, they will be providing the PDKs or process design kits for the designers, so that all the PDKs, it consists, they incorporate all the parasitics, the process variants, all the element mismatches into their models, so that the designers will be able to provide a good design, so that after fabrication, the results will come out as expected. And as I said, PDK or the process design kit, it is a collection of verified data files. It is provided by the foundry. It contains all the information for designing ICs using a specific fabrication technology. And it includes the schematic symbols, SPICE models, P cells, the design rule checks, layout versus schematic, and parasitic extraction run sets. So all these are available in the PDKs, and the foundries will be giving this PDK to us for proceeding with the design. And I think most of you have heard about GPDK, that is a generic PDK that is given by Cadence for study purpose. And the purpose of the PDK is for design validation. That is, we can ensure that the IC design is manufacturable, and at the end, the IC will function correctly as expected. And it helps the designers optimize the circuits for performance, for low power, for area efficiency, and yield based on the process technology. And so this PDK will be bridging the gap between the design team and the manufacturing process. So that is all about the PDKs. And just a glance on to the different MMIC foundries, silicon-based MMIC foundries. I think all of you have heard about TSMC, Taiwan Semiconductor Manufacturing Company. So TSMC, it provides different technology nodes from 180 nanometer, 45 nanometer, etc. And Global Foundries, they have SOI-based PDKs and SIGG-based PDKs. Tower Semi, DB High-Tech, XFAB, these are all silicon-based MMIC foundries. And a few gallium arsenide MMIC foundries, Win Semi, Corvo, OMIC, GCS, UMS. These all have gas-based PDKs, so that we can design good power amplifiers. Power amplifiers with high performance, and also LNAs with good noise figure. And GAN-based foundries are also there. Win, Corvo, UMS, OMIC, these support GAN-based PDKs. And just glance through the different tools for designing of the MMICs. The leaders are the Cadence, Synopsys, and the Mentor Graphics. Other tools are also available, but usually we go for Cadence Virtuoso for the schematic and the layout design. And the Spectre, Virtuoso Spectre is the circuit simulator. And certain tools are also available for the layouting and the parasitic extraction. And this is a photograph of a transceiver MMIC. Here you can see the total die size is 1.9 crores 1.4 square. This is an that is close to 2 crores 1.5 square. So this is a transceiver. You can see here, this is the receiver, RX1. You can see RX2. Then there will be, yeah, this is a transmitter, TX. So this is a receiver plus transceiver chip. So here the input signal coming through this LNA, then moving to the mixer, and the transmission is happening through this PA to the output filter. So this is just a photograph of an MMIC so that you can have an idea of how an MMIC looks like. Again, this is a 60 gigahertz MMIC for wireless digital communication. So in this design, there is a mixer, then a VGA, variable gain amplifier, there is a switch and an LNA. So this is the photograph of the 60 gigahertz MMIC. So that is just to have an idea about how an MMIC looks like. And moving on to the MMIC design flow. Basically, an MMIC design starts by fixing the specifications. So we'll be taking the feedback from the customers, we'll be taking the designer inputs, and we'll be taking into consideration the technology capabilities, and we'll be formulating the MMIC specifications. And after the specifications are formulated, we will go for the circuit design, and we will analyze the circuit. We'll try the optimization. Parallelly, we'll be doing the layout. In the layout section, we'll be having the EM simulators, electromagnetic simulators, and we'll be doing the EM simulation or the post-layout simulations. And parallelly, we'll be working the layout engineer and the schematic designer will be parallelly working to reduce the parasitic effects. And finally, we go for the fabrication. So this is a design approach for a typical MMIC amplifier. So basically, an amplifier design starts from the foundry PDK. So initially, we should study the capabilities of a PDK, and that PDK will be giving an n number of FETs. That is, different types of FETs will be available, like NMOS, PMOS, then RF MOS, then thin oxide MOS, thick oxide MOS. So different types of MOSFETs will be available. So initially we should have a good study of the FETs, and we should choose the right MOSFET so that we will get the required gain, noise figure, or power. And next is you should perform the DC simulations to fix the proper bias point. If it is a low noise amplifier, you will have to fix the right bias point. If it is a power amplifier, you have to fix whether it is a class A, class B, or class AB. Accordingly, you will have to fix the bias point. And if you are going for an LNA design, you have to do a noise figure analysis. Basically, it is done using the S parameter analysis. And for PA, you will have to go for a load pull analysis. And you will have to do a stability analysis. And if the stability factor is less than 1, you will have to add suitable feedback networks so that the stability is improved. Then you have to go for the impedance matching at the input and output stage. And you should properly design the DC biasing network. And after all these steps, you have to go for the schematic optimization. So in the schematic, you will be over designing the parameters. That is, if you need a gain of say 10 dB, you will be designing for a say 13 dB or 15 dB, so that after the layout simulation, it comes down to the required 10 dB. So always we will be designing for an over specified range. Like again, if it is 10 dB, you will be fixing for 13 dB. And if it is a noise figure, you will be fixing, if you need a noise figure of say 0.6 dB, you will be fixing the noise figure to say 0.4 dB, so that after layout, it comes to the required range. So after doing the layout, you will be doing the final EM simulations, electromagnetic simulations, or the post layout simulations. And finally, you will be trying to reduce the parasitic effects. And finally, you will be going for the GTS submission. So if the time permits, I will just uh, go through the different steps in the low noise amplifier design. So basically, a low noise amplifier is the first stage. As I told, in the receiver stage, the first stage is a low noise amplifier, because it is a in an RF receiver. The first stage is the main stage that determines the noise of the entire receiver system. So the low noise amplifier, it will be having a very low noise, so that low noise will be the noise of the entire system. So that is the significance of this low noise amplifier, and why it is fixed as the first stage of the receiver stage. So these are the performance variables and trade-offs associated with an LNA design. Basically, you will have to go for a low noise figure. You should have a sufficient gain for the LNA. It should have good stability. It should have good linearity. The matching should be good. But obviously, there is trade-off between all these parameters. Suppose if I'm trying to reduce the noise figure, the power consumption will increase. If I try to increase the gain, obviously the linearity will be affected. So this is again, we will have to play with the trade-offs while designing LNAs or PAs. And basically, the analysis is done using S parameters or scattering parameters. So this is a two-port network, and you will be having 4 S parameters: S11, S12, S21, and S22, where S11 and S22 are the input and output impedances. S21 is the gain, and S12 is the loss associated from port 2 to port 1. So basically, we'll be having the circuit as a black box. We'll be having only the two ports, port 1 and port 2, and analysis is done using the S parameters. And linearity, basically, it is checked using the P1 dB and IIP3. P1 dB is the 1 dB compression point. That is when when we take the input power versus output power graph, you will see at one point the gain will be reducing 1 dB from the linear plot. So this is a point where we call it as a P1 dB, that is taken as a measure of the linearity. Again, you will be having IIP3 and OIP3. These are the third order intermodulation products. These are basically set as the specification for the linearity. And again, stability. We do some simulations for the stability analysis. Basically, it is called the K parameter, the Rowlett's stability factor. So usually this K parameter should be greater than 1. If it is less than 1, you will have to add some feedback networks, some R resistors or RLC networks, so that the stability is improved. And again, matching is very important as far as an LNA or PA designs are concerned. For the case of LNA, you will have to go for minimum noise matching. So the input impedance, input matching network should be designed in such a way that the matching is done for minimum noise. So once we design for minimum noise, you will not be able to attain maximum power. But because it is a low noise amplifier, you will be designing for minimum noise. And for every designs, you should take care of the integrated circuit cost, because the IC cost, it depends upon the die area. So as the die area increases, the cost increases. So the ultimate task of the designer is to design the circuit in such a way that the area is very less, so that the cost can be reduced. And these are the design steps, as I mentioned. First, you have to select the device properly. You have to select the best MOSFET available with the PDK. The topology selection, whether it is a single transistor amplifier, or whether it is a cascade amplifier, whether it is a cascade amplifier, such type of architecture selection should be taken care of. And the DC bias design is again important. Matching circuit design is again important. And the layout, it is again another area. It is done by the layout designers, and finally to IC fabrication. So I think I will just skip the LNA, some of the slides, because it is time is rushing up. And as I said, LNA topologies, you'll be having different topologies. You will have to come upon with the right topology for your specification. So you will be having common source stage and common gate stages. In common source stage, you will be having inductive load. You can have resistive feedback networks. You are having cascade designs, inductive load and inductive degeneration. In some designs, inductive degeneration will not be required. In some cases, for the matching and for stability, you will have to add the inductors at the source. So these kind of decisions should be taken at the right time. And the DC bias design, here you are having a MOSFET, and you have to bias the FET, the gate of the FET, so that it is in saturation. So you have two options. One, you can give the bias through an inductor. Another option is you can give the bias through a resistor. Both are having its own advantages and disadvantages. So if it is an inductor, the losses will be less, the gain will be high, and the noise will be less. But because of the resonance associated with the inductor and the capacitance, it will be narrow band due to resonance. And if you are going for resistance based DC biased design, you can go, you'll get a broadband design. But obviously, because of the resistor, there will be noise. So the noise figure of the LNA will reduce. So you have to properly choose the DC bias design. And these are basic structures, basic architecture of a common source LNA with source degeneration. Source degeneration means you will be placing an inductor at the source for better matching and stability. And plus, you will be doing the DC analysis. You will be doing the current versus voltage simulations. And based on this, you will be fixing the right voltage, gate voltage, the point where we will be getting the minimum noise and good gain. We will be doing the DC analysis for fixing the bias points. And again, Smith charts are very important. The good knowledge of Smith chart is required for the proper matching for LNA, input and output. Even for PA, this Smith chart is used for proper matching. So if we are having a capacitive impedance, to make it inductive, you will have to move to the upper part of the Smith chart. And if you need a capacitive impedance, you will have to move to the lower part. So accordingly, you will have to place series inductors or parallel inductors, or series capacitors or parallel capacitors accordingly. So Smith chart will help you to design the proper impedance matching networks. And in ADS is a tool which is used for MMIC designs along with cadence. So there is a Smith chart utility available in ADS where we can design the matching networks. And this is a two-stage LNA with matching networks. If you need good gain, you can go for cascading of the stages. And so this is a two-stage LNA. And once we move on to higher frequencies, you will be using the distributed components for the design. You will be using the transmission lines, the T's, the open circuit stub, short circuit stubs, etc. for designing. And yeah, I will skip these slides and I'll move on to the MMIC design challenges. As a summary, specification finalization. Once you finalize the specs, you should compare with the available products in the market. You should be aware of the leaders. Suppose I'm designing an LNA, I should be aware of which all LNAs are available in the market and what are the specifications of the leading companies. So that I can fix my specification accordingly. And depending on the application, it changes. And the PDKs, the right PDK should be chosen, because I will be having n PDKs in front of me, but I will have to carefully study the performance of each PDK, whether it is gas or GAN. You will have to compare the power densities, you'll have to compare the noise figures, and you should do a proper selection of the PDK. And again, the architectures for the design, then the layout design is also critical. Again, coming on to the packaging. Once we do the design, you should be aware of what package. Once the chip comes out, you will have to package the die. So the packaging type and what the number of pins of the package, what is the material of the package, these all matters. And we should incorporate all these things while we do the simulation. So without these packaging knowledge, if we design, then after coming out, when we do the testing, it will be there will be a total deviation from what we have expected. And the evaluation board design is also again very important. And finally, we'll be doing the datasheet preparation. And this is what I told about the packaging. So suppose this is a QFN 16 package. QFN is a quad flat no lead package. So this is a 16 pin QFN package where here we'll be placing the die and some bond wires are connected to the lead frames. So this bond wire will be having some inductance. So these inductance should be taken care of while designing, while doing in the design stage itself. So this is what I mentioned. So this is a test bench with package parasitics. So this is my, say, LNA design. And you should simulate this LNA with the package parasitics. Here I have used two bond wire models. This will be having close to say 0.4 or 0.6 nanohenry, because the matching at the input side is very important. If you are not including these bond wire parasitics in the simulation, once the chip comes out, it will be a total failure. And again, you will have to incorporate the package capacitance also. So this should be taken care of while doing the RF designs. And finally, you should do the design with the PCB. Also in ADS, these kind of simulations setups are available. So you have to simulate the design with package and with our PCB also. So this is a summary. Always at higher frequencies, parasitic capacitance and inductance are more significant. So we should take care of all these parasitics while doing the design. And again, the temperature, you will have to fix the proper temperature of operation while doing the simulations. And the high frequency operation, you will have to carefully consider the parasitic effects. You should do the EM simulations, electromagnetic simulations, the signal integrity, everything have to be taken care of. And coming on to the conclusion, you have to use the best LNA, because LNA is the one that determines the receiver performance. You have to use the best LNA with minimum noise in your design. And again, the nominal temperature should be properly fixed. And while designing the board, you have to use the proper bypassing of the DC power supplying circuit. And again, the signal path to the LNA input, you should avoid lossy elements, because all these matters while designing the LNA. So these are my thoughts, quick introduction into the RF design. Because the time is very less. I just rushed through some of my slides, but I hope I was able to just introduce into some MMIC design related aspects. So I'm winding up for now. So over to the Q&A session. So I would like to take up some of the questions.
Yeah.
Thank you.
Thank you, Prameela. Now this floor is open for Q&A questions. So I'll ask a question like you talked about different material selection is important, right? So is
Yeah.
application how application related specifications would be the ones that we use for these kinds of like gas and GAN, right?
Yes. So basically, suppose we are going for satellite, SATCOM-based applications. It is in the, if you are going for Ka-band applications, it is in the 28 gigahertz. So in the those kind of 28 gigahertz, the CMOS will not work because we need good CMOS will not support this kind of high power densities and efficiency also. So mostly designers will be taking up the gallium arsenide and gallium nitride based PDKs for SATCOM based applications. But if it is towards the lower frequency side and if it should be cost effective, then you can go for the CMOS based design. That depends upon the application also, application frequency range, etc.
Okay, so next maybe for a novice who is just starting in this area, so LNA design would be a good start, is it? No, just for as a
basically, all the designs are independent because LNA design, it is one area, and PA design, power amplifier design, it is again another area. Mixer design is another area. PLL design is another area. So basically, LNA and PA both are amplifiers. So you can start with a basic amplifier design so that we'll be able to familiarize with the DC analysis, then the S parameter analysis. Then you will get to know about the gain, noise figure, etc. But mixer and PLL designs, those are filter designs. All are different designs. So maybe LNA design will be a good start because all the designs, the initial start will be the DC analysis, the IV. You will have to plot the IV uh, current versus voltage, and you will have to analyze which gate voltage should be supplied so that the maximum gain, minimum noise is coming. So maybe you can take up a small amplifier and start designing.
Okay. Thank you. So any further questions? Okay. Anyways, the slides will be shared and they have your contact. If there is anything further, probably a mail will do, I think. Yeah, thank you. So I would like to thank Prameela for the excellent session. So me as a novice also enjoyed this in terms of understandings because the session built up from the basics and finally the design of MMIC followed by challenges that are there and points that we have to take care while we are doing something like this. Hopefully, participants who are interested in this particular area would be able to take this forward and this knowledge and contribute significantly. So thank you, Prameela, for this excellent session and your teaching teaching experience has definitely put value to the way you have explained things in a simple way, because I know for sure that there are very few experts in this area, right? In India, probably working like this. So thank you very much, Prameela, for your time.
Thank you. Yeah.
Thank you.
So thank you,
Okay.
participants, for the patient listening. So any queries, you can get back. Okay. Thank you. Thank you so much.
Yeah.